Good evening, everyone. So, we have been discussing electrochemistry, right? We have started with electrochemistry. Could you please recap the last session? Send Chelvan. Could you please tell me the topics we have discussed in the last class? So, shall we do it together?
Yes, madam. Because they lost touch for 4, 5,
Okay.
2, 3 weeks. So I think you can
Okay, sir.
restart it.
Okay, sir. Yeah. Harshita, is this your first class?
Yes, ma'am.
You are from 11th or 12th?
Sorry.
Which class you are in? Harshita, which class you are in? 11th standard or 12th
I'm
standard?
standing in I'm studying in 11th standard.
11th standard. Okay, you
Yes,
are
ma'am.
from? Where are you from, Harshita?
Coimbatore, ma'am.
Coimbatore. Okay, fine. So, last class we have started with a chapter called electrochemistry. So, in which we have studied few fundamentals like what is chemical energy, what is electrical energy, what is the difference between spontaneous reaction, non-spontaneous reaction, and we have discussed what is cell and different types of cells. Actually, there are two types of cells based on the chemical reaction which is occurring inside the cell. And after which we have touched the redox reaction concepts, like what is oxidation, what is reduction, what is redox reaction, oxidizing agent, reducing agent, and all that. And we have seen a few questions also from redox reaction. So today we're going to get into the chapter in depth. So please, this electrochemistry chapter is very important. It is important in your board point of view, and also it is very important in your entrance exam point of view. But solving the questions from electrochemistry, for which you have to be very, very strong in concepts. So please concentrate on the concept. Please don't memorize anything. So understanding the concept is very important. So for that, this class will be really helpful. Okay, if you don't understand anything, please let me know. I'll help you. So let me share the screen. Is the screen visible? Is the screen visible? Bhumika, is the
Yes,
screen
ma'am.
visible now? Okay, Harshita, right. Fine. So electrochemistry is from 12th standard, but uh, people who are from 11th standard, please don't worry. Anyways, we're going to start from the fundamentals. So if you are in 11th standard, please don't worry. Even though you're in 11th standard, definitely you can understand this chapter, okay? Anyways, you're studying the chapter in advance, that's it. So definitely you'll understand the concept. So please listen carefully. Electrochemistry. So in this chapter, as I've told you already, in this chapter we'll be discussing the working mechanism, which is actually happening in cells and batteries. Usually we are using cells and batteries in electronic devices, right? So in this chapter, we'll be discussing what kind of chemical reactions are happening in batteries and cells. Okay, fine. So in last class, we have discussed what is cell, right? So what is cell? It is an electrochemical device. So actually, you have to visualize cell as a device where chemical reaction is happening. That's it. So it is a device where chemical reaction is happening, which is called cell. But that kind of chemical reaction can be a spontaneous reaction or a non-spontaneous reaction. So based on the spontaneity of the chemical reaction, cell can be classified into two types. Basically, what is spontaneous reaction? What is spontaneous and what is non-spontaneous reaction? So I don't want any definition. Please tell me how you understood the concept. So what is spontaneous reaction? What is spontaneity? If a chemical reaction is happening by itself, then that is called spontaneous reaction. Then what is non-spontaneous reaction? If the chemical reaction is happening by itself, then that is called spontaneous reaction. So what is non-spontaneous reaction? What is non-spontaneous reaction? It is just the opposite, right? If the chemical reaction is not happening by itself, then that is called non-spontaneous reaction. Guys, why you're so quiet? See, as I told you already, I don't expect any perfect answers from you. I want you guys to interact with me, that's it. Bhumika,
Ma'am,
Bhumika, you attended last class, right? You were in my last class, right, Bhumika?
yes, ma'am.
Okay. Kanna, I want you guys to respond. Okay. Even though you are telling any wrong answer, no issues. Please respond. Okay. Not only Bhumika, I want everyone to interact with me, please. Fine. So, spontaneous reaction is a chemical reaction which can occur by itself, which is called spontaneous reaction. In a cell or in a device, if there is a spontaneous reaction occurring, then that kind of cell is called electrochemical cell. In a cell, if the chemical reaction is happening by itself, then that is called electrochemical cell, or it is also called as, see this, these are all the stuffs we have discussed in the last class itself. So electrochemical cell is also called as galvanic cell, or it is also called as voltaic cell. In a cell, if the chemical reaction is not happening by itself, or if the cell contains non-spontaneous reaction, then that kind of cell is called electrolytic cell. Okay. So in electrochemistry, first 70% of the chapter is basically from electrochemical cell. And last 30 chapter, we'll be discussing this electrolytic cell. Okay. So if a chemical reaction is not happening by itself, then that is called non-spontaneous reaction. And for all non-spontaneous reaction, the sign of delta G will be, what is delta G? It is change in Gibbs free energy, right? So what will be the sign of delta G? For non-spontaneous reactions, sign of delta G will be positive. And for electrochemical cell, the chemical reaction can happen or can occur by itself. So for that kind of reaction, delta G will be negative. And here, some chemical reaction will happen itself, because of which chemical energy will be generated, and that chemical energy will get converted into electrical energy. So this chemical reaction leads to a current. So this is electrochemical cell. But it is just the opposite in electrolytic cell, where the chemical reaction will not happen itself. So for that kind of chemical reaction to occur, we have to supply a particular amount of energy, and in this case, the energy what we're going to supply is electrical energy, which is current. And this electrical energy will get converted into chemical energy. Okay. So this is the basic fundamental we have to know in terms of cell and its types. Okay. Now we're going to discuss the working principle of galvanic cell. So from today onwards, we're going to get deeper into the chapter. Please listen carefully. So, as far as electrochemical cell or galvanic cell is concerned, we have so many types of or so many examples for this galvanic cell, in which we're going to discuss one cell which is called Daniel cell. So, Daniel cell is a kind of galvanic cell. So, what is galvanic cell or what is electrochemical cell? What is Daniel cell or electrochemical cell? So, in that kind of cell, what kind of chemical reaction will occur?
Spontaneous reaction, ma'am.
Very good, Harini. Spontaneous reaction. So now we're going to understand how the spontaneous reaction is giving us the current. Okay. So Daniel cell is one of the examples of galvanic cell, and we're going to see how Daniel cell is working. Okay. So before getting into the complete working principle, first we're going to construct the cell. Okay. First I have a beaker, and in this beaker I'm going to dissolve a salt called zinc sulfate. So now I'm going to dissolve zinc sulfate salt into this beaker which contains water. Okay. So basically zinc sulfate is a salt which is in solid state, and if you dissolve the zinc sulfate salt into water, it will get dissociated, right? So how this zinc sulfate salt will get dissociated into water? It will get splitted up, right? So how the zinc sulfate salt will get dissociated? Zn2 plus and SO4 2 minus. Okay, so the zinc sulfate salt is getting dissolved in water to form ions like Zn2 plus ion and sulfate ion, which is SO4 2 minus. So these two ions are dissolved inside aqueous solution. That is what here I've represented, like AQ. Okay. So basically, zinc sulfate is a salt, and I'm dissolving the zinc sulfate salt into water, because of which few ions are generated inside the solution, right? So if this chemical compound is dissolved inside any aqueous medium, if that chemical compound releases these kind of ions, then that chemical compound is called an electrolyte. So electrolyte is nothing but a chemical species which dissociates into ions in the aqueous medium. Okay, so zinc sulfate is an electrolyte. Okay, so electrolyte is a chemical compound which dissociates into ion in aqueous medium, which is called electrolyte. So in this case, zinc sulfate salt is an electrolyte, because when we are dissolving the zinc sulfate salt inside this aqueous medium, zinc sulfate salt dissociates into Zn2 plus and SO4 2 minus ion. Okay. So now I've dissolved this electrolyte inside the solution. Now the solution is called as an electrolytic solution. Electrolytic solution, and this electrolytic solution contains lot of Zn2 plus ion and SO4 2 minus ion. So this is an electrolyte and this is an electrolytic solution into which I'm going to dip a metal. Could you please tell me which metal is related to zinc sulfate salt? Here we have two ions, right? One is zinc ion and another one is SO4 2 minus ion. Could you please tell me which metal is related to this salt? Obviously zinc metal. Okay, I'm going to dip a zinc rod inside this solution. So zinc sulfate salt is electrolyte, and I've dissolved the zinc sulfate salt inside the solution, and the solution is called electrolytic solution, and into which I'm going to dip a metal which is zinc, and this is called electrode. So in this cell, I've constructed the half cell. Okay, in Daniel cell, I've constructed the half cell, and now I'm going to construct another half of the cell, and I'm going to connect both the halves. Okay, so in one beaker, I have zinc sulfate solution, which is called as an electrolytic solution. Similarly, I'm going to take another beaker, and in this beaker, I'm going to dissolve copper sulfate salt. What is the color of copper sulfate? What is the color of copper sulfate?
Blue.
Very good.
Blue.
Yes, Harshit, that is blue color. Now I'm going to dissolve this copper sulfate salt inside water. So it will get dissociated into copper 2 plus and SO4 2 minus ion. Since it is dissolved in aqueous medium, I'm going to represent it as AQ. Okay. So now the zinc sulfate salt dissociated into ions in aqueous medium. So this copper sulfate is called as electrolyte. And again, the solution is called as an electrolytic solution. Whenever we are preparing any solution, we'll be preparing it in a particular concentration, right? Here, the concentration of the solution is 1 molarity. And here also, the concentration of the solution is 1 molarity. So, I have a electrolytic solution. Now, I'm going to dip a metal which is related to this copper sulfate salt. Could you please tell me which metal is related to the salt? In zinc sulfate solution, I've dipped zinc metal. In copper sulfate solution, I want to dip
Copper, ma'am.
Copper.
very good copper metal. That's it. So here, this copper is called an electrolyte. That's it. So this is the second half of the cell. Now I'm going to connect these two electrodes. I'm going to use a conducting wire to connect these two halves. Here I'm going to have a voltmeter. Okay. From this voltmeter, I can see the deflection. I can see the potential difference between zinc and copper. Okay. As we know, Daniel cell is the it is a kind of galvanic cell, and here chemical reaction going to happen, and because of that chemical reaction, some current will be generated or potential will be generated, right? So we have to know how much potential was generated. So to measure the potential which was generated, I've connected a voltmeter. Fine. Now let us understand what kind of chemical reaction going to occur here. See, left side I have two types of chemical species. One is zinc, which is in solid state. Another one is zinc 2 plus, which is in aqueous medium. Okay. So whenever I'm talking about zinc, you have to visualize that I'm talking about the atom which is present in the rod. Whenever I'm talking about Zn2 plus ion, I'm talking about the species which is dissolved inside the solution. Zn cannot be inside the solution and Zn2 plus cannot be on the rod. Okay. If I'm talking about Zn2 plus, then definitely it is inside the solution. And whenever I'm talking about zinc, it is on the rod. It is basically a solid system. Okay, fine. So actually, what is happening in the left half of the cell is a zinc, which is present here on the rod. See here, the chemical reaction is happening in this region, where the solution and the electrode are in contact. Only here the chemical reaction is happening. Actually, what is happening here is the zinc, which is present on the rod, is getting oxidized. What is mean by oxidation? What is mean by oxidation? What is oxidation? Last class we
Uh,
have seen
Reaction of oxygen with another metal, with one metal.
okay, right. So addition of oxygen is
Loss of
oxidation. Very good, very good. Yes. So addition of oxygen, removal of hydrogen, or loss of electron is called oxidation. Here we are talking in terms of electrons. So here the zinc which is present on the rod gonna lose its electron. So when zinc is losing its electron, it will get converted into Zn2 plus, right? As I've told you already, the zinc, if it is in zero oxidation state, it will be on the rod. But here, zinc is getting converted into Zn2 plus ion by losing its electron. So what will happen to the Zn2 plus ion? Immediately it will get dissolved inside the solution. So the electron which was lost by zinc will get accumulated on the rod. So not only one zinc, there are lot of zinc atoms on the rod, right? So each zinc atom will lose its electron and the electrons which are on the rod, the electrons will get accumulated on the rod, and the zinc which is getting converted into Zn2 plus will get dissolved inside the solution. So at one point of time, what will happen to the rod? What is the charge of electron? What is the charge of electron basically? Is it positive or negative? Negatively charged species.
Negative.
Negatively charged species, right? So when each zinc atom is losing its electron and zinc atom are getting converted into Zn2 plus and it is getting dissolved inside the solution. And these electrons which was lost by the zinc was keep on accumulating on the rod, right? So since electrons are negatively charged species, this electrode will get a negative charge completely. Okay, so here electrons are accumulated on the zinc rod because electrons are accumulated and we have a negative charge on the zinc, right? Here in this electrode, oxidation is happening, right? In an electrode, if the oxidation reaction is occurring, then that kind of electrode is called anode. Okay, now in Daniel's cell, zinc is acting as an anode where zinc is getting oxidized. Okay, and similarly, see, left side oxidation is occurring, so electrons are accumulated on the zinc, so electrons are rich on zinc. Relatively, compare the right side. Here there is no electron, here electrons are accumulated, so what electrons will do? Here electrons are rich and right side there is no electron. So what these electrons will do? It will start moving, it will move from zinc rod to copper rod because here electrons are accumulated and here in copper there is no electron. So at one point in time, all these electrons will be moving from zinc rod to copper rod, right? So this is the direction of electron. As we know, this is the conducting wire. So obviously electrons can move from zinc to copper rod. Now these electrons are getting accumulated here. Now what will happen is copper 2 plus ion. Actually, where this copper 2 plus ions will be? Copper 2 plus ions will be in solution or on the rod. Where this copper 2 plus ions will be?
In the solution, ma'am.
Inside the solution, right? So when these electrons are getting accumulated on the rod, copper 2 plus ion which is present inside the solution will gain 2 electrons. So one copper 2 plus ion will gain 2 electrons. So it will get reduced to so each copper 2 plus ion will gain 2 electrons. So it will get reduced to I have two positive charge on copper, and this two positively charged copper is gaining two electrons. So what will be the charge on copper? What will
Neutral.
be neutral? That's it. So when copper 2 plus ion is there, it will be inside the solution. But now copper 2 plus ion is gaining electron and it is getting reduced to copper atom. So here in left side, the zinc atom which was present on the rod started getting dissolved inside the solution. And contradictorily, right side, the copper 2 plus ion which is inside the solution is gaining electron. It is started getting deposited on the rod. Okay. So left side, the electrode which is present on the left is losing its electron. So oxidation is happening. The electrode which undergoes oxidation is called anode. And in right side, in copper, copper 2 plus ion is gaining electron. And here in this electrode, reduction is occurring. The electrode which is undergoing reduction is called cathode. And what will be the sign of cathode? Here initially electrons were accumulated on the electrode or on the anode, so it was negatively charged. Since here electrons are rich and right side, initially there was no electron, right? So it is positively charged. Okay, that's it. So here In zinc, electrons was lost and oxidation were happening, and the electrons which was accumulated on the zinc rod were started moving from zinc rod to copper rod, and in copper rod, electrons were gained and it was deposited. That's it. So till now, do you have any doubt? Do you have any doubt? See, we didn't complete working principle yet, but do you have any doubt till now?
No, ma'am.
Okay. So basically, what is current? Flow of charged particle in a particular direction, right? Here, charged particle is electron, and these electrons are moving from zinc to copper. So basically, here the electrons are moving from left to right. So obviously, we'll be expecting current, right? So what will be the direction of current? Last class we have discussed the direction of electron flow and the current flow, right? It will be just opposite to each other. So here electrons are moving from zinc to copper. So what will be the direction of current? Where current will be moving? From which
To
direction to which
zinc.
direction?
Copper to zinc.
That's it, copper to zinc. So when these electrons are moving from zinc to copper, we'll be expecting current moving from copper to zinc. But actually, current is not generated it. In physics lab, you would have observed that for any current to flow in a circuit has to be closed, right? So let us see whether the circuit is closed or not. See, electrons are generated here, and these electrons are moving from zinc to copper through this conducting wire. Now, here we got electrons, right? But the circuit is not closed yet. Since the circuit is not closed, current were not generated. So, to generate the current, we have to close the circuit. So, how to close the circuit? Basically, electrons are generated here and it is moving from left to right, but there is no connection between these two beakers, right? So I'm going to connect these two beakers. So to connect the beaker, what I'm going to use is a bridge. So it is like a U-shaped tube. And inside this tube, I have a salt. See, we cannot use any type of salt in this bridge. There are only few types of salts we can use here. I'll tell you the condition later. I'm going to have a salt called KCl. What is the name of KCl?
Potassium
Potassium
chloride.
chloride.
ma'am.
Very good, potassium chloride. So I'm going to have potassium chloride salt. Obviously, salt will not stand, or generally it will not stay inside this inverted tube, right? So I'm going to mix the salt in a gel called agar-agar gel. So I'm going to mix potassium chloride in agar-agar gel, and I'm going to fill this inverted U-shaped tube. Okay. Now I've connected these two beakers and I've completed the circuit, and definitely current will flow from copper to zinc. That's it. See, there are two main roles of this green color bridge, and this bridge is called salt bridge. Why it is called as bridge? Because we are connecting these two beakers. So it is called bridge, and this bridge is filled with salt. So that is why it is called as salt bridge. And we cannot use any salt inside this salt bridge. There are only few salts which can be used, and I'll tell you the condition for the salt to be filled here. Okay. Before getting into the condition, let us understand the role of the salt bridge. The first role is to complete the circuit, right? Second role is to maintain the electrical neutrality in zinc sulfate solution and in copper sulfate solution. So let us understand that. Guys, listen. Can I listen carefully? Initially, in this beaker, I've dissolved copper sulfate salt, right? So while I'm dissolving this copper sulfate salt inside the solution, we ended up with Zn2 plus ion and SO4 2 minus ion, right? So if 100 Zn2 plus ion was generated, then similarly 100 SO4 2 minus ion were also generated, right? So here the ratio was 1 is to 1. Number of cations and number of anions produced inside the zinc sulfate solution was equal. So basically it was neutral, right? And in copper sulfate solution also, while I was dissolving copper sulfate salt inside the solution, the ratio is 1 is to 1, right? You guys getting my point? What is this 1 is to 1 ratio? What is this 1 is to 1 ratio? Number of cations produced are equal to the number of anions produced, right? If 1000 copper 2 plus were generated, then similarly 1000 SO4 2 minus were also generated. So basically it was neutral initially, right? When copper sulfate was dissolved inside the solution is neutral. And similarly, if you are dissolving zinc sulfate solution, that was also neutral, right? Initially, before the chemical reaction is happening, both the solution were in neutral condition. Okay. Now, after dipping the copper rod in copper sulfate solution and after dipping zinc rod in zinc sulfate solution, I've connected both the rods using a connecting wire, right? So after connecting these zinc and copper rod, what happened in zinc sulfate solution? What kind of chemical reaction were happened in zinc sulfate solution? What chemical
Oxidation
happened?
reaction.
Very good. Oxidation reaction, right? So in oxidation, zinc atom which was present inside the rod were started getting oxidized, which means it is started losing its electron, and zinc rod were started dissolving inside the solution. For example, initially I had zinc ions as 100. I'm going to tell you the hypothetical number. If I dissolved zinc sulfate solution, initially let us say zinc ion were present inside the solution is 100. But if during the oxidation process, zinc atom was dissolving inside the solution as Zn2 plus ion, right? So how this concentration will get changed? Zinc 2 plus ions concentration will get increased, right? Because zinc atom which is on the rod is getting oxidized and it is getting converted into Zn2 plus and it is keep on dissolving inside the solution, because of which the concentration of Zn2 plus ion inside the solution was rising. So here the neutrality was disturbed. Initially, the concentration of Zn2 plus ion and concentration of SO4 2 minus ion. That is, the concentration of cation and anion were equal, and it was neutral initially. But during this oxidation process, the number of cations inside the solution is getting increased. So neutrality was disturbed, right? Similarly, what is happening in the copper sulfate solution? Reduction, right? So during this reduction process, what happened? During this reduction process, what happened? Which was getting reduced, which was getting reduced in copper sulfate solution.
Copper is getting reduced, ma'am.
Yes, the copper 2 plus ion, which is already in the solution, got reduced and it is it is getting deposited on the rod. So let us say initially I had 100 copper 2 plus ion inside the solution, and during this reduction process, the ions which is present inside the solution is getting deposited, because of which the number of copper 2 plus ion was decreased, right? Initially, copper 2 plus ion is 100 and SO4 2 minus ion is also 100. They were neutral. But during this reduction process, copper 2 plus ion inside the solution is getting decreased, right? Because of which anions count is getting increased, right? So here also neutrality was disturbed. So in zinc sulfate solution, cation was increasing, and in copper sulfate solution, anion was increasing, because of which neutrality was disturbed. Okay, now here comes the role of salt bridge. See, here in salt bridge, I have potassium chloride salt. So how this potassium chloride salt will get dissociated? K plus and C minus, right? whenever in zinc sulfate solution, zinc ions concentration is getting increased, that is cations concentration is getting increased, we have to maintain the neutrality. Here cations concentration is getting increased, right? So to maintain the neutrality, anions concentration also has to be increased. In potassium chloride salt, Cl minus is the anion, right? So the Cl minus ion which is present inside the salt bridge will get started dissolving inside the solution. So because of which cation and anion's concentration will be equal and neutrality can be maintained. And similarly, in copper sulfate solution, anion's concentration is getting increased, right? Because copper sulfate is getting deposited on the rod. So to maintain the neutrality, cation has to get dissolved. Here, what is the cation? Potassium plus. So K plus will be dissolved inside the solution to maintain the neutrality. Okay. So salt bridge got two roles. One is to complete the circuit and another one is to maintain the neutrality between zinc sulfate solution and copper sulfate solution. Okay. And as I told you already, we cannot use any salt inside the salt bridge. There is a particular condition. See, here potassium ion is moving towards copper sulfate solution and chloride ion is moving towards zinc sulfate solution, and the ionic mobility of cation and anion has to be equal. See, all the in all the salts, ionic mobility of cations and anions will not be equal. Only in specific salts, cations mobility and anions mobility will be equal, and only that kind of salt can be used in salt bridge. Okay, so potassium chloride is one of its kind. Okay, so in potassium chloride, ionic mobility, that is ability to move, the ability of the ions to move is called ionic mobility. Ionic mobility of cation and anion has to be equal. That kind of salt can only be used in salt bridge. Okay, so here we have a complete cell. I've completed the cell using the salt bridge. So because of which current is generated and the volt was measured in this voltmeter. Okay. Here, left side of the cell, we have oxidation. Right side of the cell, it was reduction. And the electron was generated in the anode and the electron were moved from anode to cathode. So because of the mobility of electron, current was generated and the current generated was moved from cathode to anode. Because of this current flow, there is a change in voltage. And here, the volt generated was 1.1 volt. Okay, see, this is the standard value for Daniel cell. Here, volt is the unit, and here it is the potential, right? So potential is represented with the alphabet capital E, and it is the potential of cell, so it is called E cell. And the cell is in the standard condition. See, they'll ask you the standard condition of cell. Actually, standard condition is nothing but we have to specify the temperature, pressure, and concentration. Temperature has to be 25 degrees Celsius and pressure has to be 1 atmosphere, and most importantly, the concentration of the electrolytic solution has to be 1 molarity. And as I told you already, both the concentrations were 1 molarity each, right? So the cell is in standard condition. So the the potential I've generated here is E naught cell. Standard cell potential of Daniel cell is 1.1 volt. Okay, so this is the working principle of Daniel cell. So this working principle is very important. If you understand this working principle, rest of the chapter will be very easy. Okay, you're getting the point. Any doubt? Please ask me. If you have any doubt, please ask me, Karna. Any doubt?
No, no.
Okay. So shall we proceed? Shall we proceed to the next concept?
Yes,
Right.
ma'am.
So here I've discussed the okay, Tata. So I've discussed the working principle of Danielson. So Daniel cell is a kind of galvanic cell where chemical reaction will happen itself. See here, I've just connected the zinc rod and copper rod, and I didn't do anything. Chemical reaction, which is called oxidation and reduction, happened by itself. And because of this chemical reaction, current was generated, and I've represented it in terms of potential, which is 1.1 volt. See, E naught cell is the representation. See, not represent the cell is in standard condition, and capital E represents potential, and in subscript I've written cell, right, which means it is the potential of the cell, and the cell is in standard condition. That is why I've represented with not symbol. And here the value is 1.1 volt. It is a standard cell potential of Daniel cell. Okay, right. See, in chemistry, though any process is happening anywhere, we can represent that process in a single line, which is called chemical equation, right? Similarly, any type of cell can be represented in a single line, which is called cell representation. Cell representation. From the cell representation, we can understand which is anode, which is cathode, where oxidation is happening, where reduction is happening, and what is the sign of each electrode and all that. Okay. So let us see how to represent any cell. Okay. So here in cell, at the middle of the representation, we'll be having two parallel lines. And this two parallel lines represents salt bridge. Okay. And from this diagram, please tell me, in salt bridge, left side what we have, what electrode we have, left side what electrode we have, left side to the salt bridge,
Zinc.
anode,
Anode, ma'am.
right? And right side we have cathode. Yes. So this is salt bridge. Left side we should have anode, and right side we should have cathode. That's it. So here I'm going to represent this Daniel cell. So in Daniel cell, we have salt bridge, and left side I'm going to write anode. As far as Daniel cell is concerned, zinc is the anode, right? In anode side, we have two chemical species. One is zinc, another one is Zn2 plus. See, zinc is in solid state and Zn2 plus is in aqueous medium. So they are two different physical states, right? So I'm going to differentiate zinc from Zn2 plus by using a single vertical line. Single vertical line represents phase boundary. One is salt, one is in solid state, another one is in aqueous medium. Okay. So among zinc and Zn2 plus, which is the most reduced form? Which is the most reduced form? Reduced form represents the species with more number of electrons. Among
Zinc, ma'am.
very good, zinc. So the most reduced form will be at the leftmost corner, and Zn2 plus will be here, which is an aqueous medium. And what is the concentration of the solution? 1 molarity. That's it. And similarly, in cathode side, we had two chemical species. One is zinc, which is in solid state, and copper, which is in solid state, and the copper 2 plus, which is in aqueous medium. And there are two different physical states, and I have to represent or differentiate using a single vertical line, which is called phase boundary. Among copper and copper 2 plus, which is the most reduced species?
Copper 2
Which is the
plus.
most reduced? The species which is having more number of electrons is considered to be the reduced one.
Zinc, ma'am.
Copper, right? So the most reduced species will be at the rightmost corner. So here copper is the most reduced species, and copper 2 plus will be here. Okay, and what is the concentration of copper 2 plus ion? Again, 1 molarity, right? That's it. So this is the cell representation. So from cell representation itself, we can understand which is anode, which is cathode. So left side will be having anode where oxidation is happening. Right side will be having cathode where reduction is happening. That's it. So instead of copper 2 plus, we can also write it as how this zinc, copper 2 plus and zinc 2 plus can be replaced with the salt which we used actually. So there we use zinc sulfate salt, right? And no, whose concentration is 1 molarity, double vertical line. The salt, what we use is copper sulfate, whose concentration is 1 molarity again, single vertical line, copper. So we can represent salt rich like this, also like this. Okay. Any doubt? Any doubt? Fine. So this is the cell representation. Now we're going to see what kind of chemical reactions were actually happened in anode, cathode, and in overall cell. Okay. In Daniel cell, in anode, what kind of chemical reaction occurred? In Daniel cell, in anode, what kind of chemical reaction occurred?
Oxidation, ma'am.
Oxidation, very good. So which species was oxidized? Which species was oxidized?
Zinc, ma'am.
Zinc, ma'am.
Very good, very good. Zinc, which was in solid state, was lost its electron and got converted into Zn2 plus. So this is the oxidation reaction. And in cathode, it was reduction, which was reduced copper 2 plus ion, which was present inside the aqueous medium, gained 2 electron to get converted into copper. So copper 2 plus ion gained 2 electron. So copper 2 plus ion in aqueous medium gained 2 electron to get converted into copper, which is in solid state. So this is anode reaction and this is cathode reaction, and we're going to write the overall cell reaction. So to find the overall cell reaction, what we have to do? We have to add both the reactions, right? So overall cell reaction. So to add both the reaction, first check for the common species. Here, in first reaction, we have to match the left side of the first reaction and right side of the second reaction. Is there anything common? No. In first reaction, left side we have zinc, and in second reaction, right side we have copper. Nothing is in common, so we cannot cancel anything. But in first reaction, right side we have Zn2 plus an electron, and in second reaction, left side we have copper 2 plus ion and 2 electrons. So we have 2 electrons in common, so we're going to cancel both the electrons. Now we're going to add both the reactions. So in first reaction, left side we have zinc, which is in solid state, and in second reaction we have copper 2 plus ion in aqueous medium. That's it, right? Which gives right side. Could you please tell me the species which is on the right side?
Copper in solid state, zinc 2 plus in aqueous.
That's it. So in anode, oxidation, and in cathode, reduction. But overall cell reaction is a redox reaction, because in this zinc was getting oxidized and copper was getting reduced. So the reaction which is happening in cell is a redox reaction basically. Okay. So for any reaction, you have to write this anode reaction, cathode reaction. So you have to know how to write this anode, cathode, and overall cell reaction for any cell given. Okay. Do you have any doubt till now?
No, ma'am.
Okay. See, before getting into next concept, we have to know a few things. Okay. As I told you already, there are two types of cells. Right? One is a galvanic cell, another one is electrolytic cell. In any cell, we'll be having two electrodes. One is anode, another one is cathode. And first 70% of the chapter is about galvanic cell. And last 30 will be electrolytic cell. But in both the cells, we'll be having anode and cathode part. Okay, in any cell, we'll be having anode and cathode. But the sign of anode and cathode will differ from differ for both the cells. Okay, so to make it clear, I'm going to have a tabular column. Please listen. In any cell, we'll be having anode and cathode. See, in Daniel cell, we had anode and cathode, no? So similarly, in any cell, though I mean, can be electrochemical cell or your electrolytic cell, we'll be having anode and cathode. Whatever the cell is, in anode, oxidation will occur, and in cathode, reduction will occur. There is no change in it. Okay. Uh, if the cell is galvanic cell, galvanic cell is also called as electrochemical cell or voltaic cell. Then sign of anode will be, what will be the sign of anode? We saw in Daniel cell, right? What was the sign of anode? Sign of anode in Daniel cell. In anode, what reaction occurred?
Oxidation, ma'am.
Oxidation, where zinc atom, which was on the rod, got uh, got converted into Zn2 plus, and it was dissolved inside the solution, and the electron which was lost by the zinc was accumulated on the anode, right? So because of which anode got which charge?
Yeah, yeah,
Negative charge, ma'am.
Negative charge, right? So not only in Daniel cell, but in all galvanic cells, anode will have a negative charge because in anode oxidation were happening, because of which electrons were accumulated on the anode. Since the electrons are negative charge, anode will also be negative charge. Okay, and similarly, cathode reduction were happening, and the sign of cathode was positive. Okay. And we know why anode got negative charge and cathode got positive charge in galvanic cell. Next type of cell we're going to discuss in the future is electrolytic cell. There also we'll be having anode and cathode, and in anode oxidation and in cathode reduction. But the sign of anode will be positive and sign of cathode will be negative in electrolytic cell. While we were discussing electrolytic cells working principle, I'll tell you why this anode got positive charge and anode got negative charge in electrolytic cell. But don't get confused. Now we know why this anode in galvanic cell got negative charge and cathode in galvanic cell got positive charge. We just stop there. In electrolytic cell, we'll discuss it in the future. Okay, now we don't get confused. Fine. Do you have any doubt till now?
No, ma'am.
Okay. One more. Okay, Kana. One more tabular column. See. What is spontaneous reaction? What is spontaneous reaction? If the chemical reaction is happening by itself, then that is called spontaneous reaction, right? What will be the sign of delta G for spontaneous reaction? What is the sign?
Negative.
Very good. Sign of change in Gibbs free energy will be negative for spontaneous reaction, and for non-spontaneous reaction, it must be positive. In a cell, if we have spontaneous reaction, then sign of E cell will be just the opposite. It will be positive. Okay. Here in Daniel cell, we had spontaneous reaction inside the cell. Right. Here, overall, in the cell, the sign of delta G will be negative. And what was the sign of E naught cell? It was positive, right? It is just the opposite of delta G. And similarly, what will be the sign of E cell for non-spontaneous reaction? If delta G is negative, then E cell will be positive. For non-spontaneous reaction, delta G is positive. Then what will be the sign of E cell then?
Negative.
Negative. Negative. Okay. So we may expect questions from like this also. They'll give you any chemical reaction and they may ask you to find whether the reaction is spontaneous or non-spontaneous reaction. So for that kind of question, you have to find the value of E cell or E naught cell, and from the sign of E naught cell, we can find whether the reaction is a spontaneous or non-spontaneous one. Okay, fine. So we are done with working principle of a Daniel cell, and we have done with cell representation, and we learned how to write the overall cell reaction. Fine. Now we're going to get into another very important concepts like electrode potential. Kanna, what is this? How you'll read this one? How you'll read this representation? What is E? What is E?
Potential.
Very good. It is potential. Potential of what?
Cell.
Very good. Potential of cell. And what this not represents?
Standard.
potential.
The cell is in standard condition. Cell is in standard condition. Okay. Could you please tell me what is standard condition?
Temperature should be 25 degrees Celsius.
Hmm.
Pressure 1 atmospheric.
Hmm.
Pressure 1 atm, ma'am.
Hmm.
Concentration 1 molarity, ma'am.
Very good. One molarity. Okay, this is very important. One molarity. Right. What is this?
Potential of cell at non-standard condition, ma'am.
Very good. It is under non-standard condition. So if the cell is in non-standard condition, then concentration will not be equal to 1 molarity. Okay, so this is non-standard condition. Fine. Right. Listen, I have few questions to ask you. Kanna, here we have used two metals in Daniel cell, right? One is zinc and another one is copper. And I've told you if you connect zinc and copper to each other, in zinc oxidation was happening and in copper reduction was happening, right? This was the statement I've told you, right? But in exam, other than this copper and zinc, they may give you any two metals and they may ask you which metal will get oxidized and which metal will get reduced. So you have to answer that kind of question. Okay. And also, here I told you the standard cell potential was 1.1 volt. If the metal is zinc and copper, then the value is 1.1 volt, which is a standard one. But if we have two different metals other than zinc and copper, or if you connect zinc with some other metal, or if you connect copper with some other metal, then definitely value will not be 1.1 volt. And in exams, they may ask you to calculate the E naught cell. So to understand which metal will act as anode and which metal will act as cathode, and to calculate E naught cell of any cell, then you have to understand few more concepts, which is what we're going to discuss now. Okay, shall we proceed?
Yes, ma'am.
Yes, ma'am.
Fine, Kana. See, we got this 1.1 volt in overall cell, right? So for this 1.1 volt, the value was contributed or the potential was contributed by both zinc and copper. But the contribution was not 50-50. The contribution from zinc was different from the contribution from copper. Okay, so we have to understand how how each metal is gaining potential, and how this each electrode is contributing to the overall cell potential. Okay, so here 1.1 volt is the overall cell potential, but to this overall cell potential, each electrode were contributed their potential, which is called electrode potential. Okay, so now we're going to see electrode potential. Here also we are talking about potential, so it is capital E. Here we will not write anything at the subscript, so that represents just the potential of electrode. If it is E naught, then the electrode is in standard condition. Okay, so it is just E, then it is electrode potential at non-standard condition, and if it is E naught, then electrode potential at standard condition. See, don't get confused with electrode and cell. Two electrodes combines together to have a cell. Okay, so each cell will have two electrodes. We have seen the potential of cell till now. Now we're going to see the potential of each electrode. Okay, let us say any metal. For example, I have zinc metal. Okay, I have zinc rod or zinc metal, and I'm going to dip this metal inside its own electrolytic solution. What is electrolytic solution? If you are dissolving any salt and if that salt is getting ionized, then that is called electrolyte, and that solution is called electrolytic solution. Here I am going to dip this zinc rod inside a solution, inside a inside an electrolytic solution of zinc. So which means this electrolytic solution should have Zn2 plus ion. So here zinc rod was dipped inside its own electrolytic solution. Okay. Generally, I have a metal M, and this metal M is dipped in its own electrolytic solution, which means the solution will have metal ions. Okay. So if it is zinc, then ion should be Zn2 plus. If it is copper, then the ion should be, if I'm yes,
2 plus.
copper 2 plus. That's it. If it is silver, if I'm dipping silver metal, then what should be the ion inside the solution?
Ag2 plus.
Ag plus. Okay, very good. Now, if you are dipping any metal inside its own electrolytic solution, then chemical reaction will occur at this region. So the region where solution and the rod were in contact. So in some kind of metal, we can expect a oxidation reaction. In some kind of metal, we can expect a reduction reaction. That depends upon the nature of the metal. Okay, a few metal will get oxidized, few metal will get reduced. Okay, if the metal is getting oxidized or if the metal is getting reduced, anyway, we'll have a charge separation there. See, for example, zinc was getting oxidized. So what is oxidation? Zinc will lose its electron, and the electrons which was lost by the zinc will accumulated on the rod, and copper will get converted into copper 2 plus ion, and it will get dissolved inside the solution. See, dissolving doesn't mean zinc will Zn2 plus ion will go somewhere inside the solution. It will be at the vicinity of the electrode. It will be very near to the electrode. Okay. So the electrons which was lost by the zinc was here, and the Zn2 plus ions were here. See here we have negative charge and positive charge, which was separated by a particular distance, which means a potential difference were generated. So this potential difference is the electrode potential. The potential difference developed in this electrode is called electrode potential. And we have two types of electrode potential. Here, the metal was oxidized, right? So the potential which was developed because of oxidation, then that is called oxidation electrode potential. Or it is also called as oxidation potential. As I told you already, few metals may get reduced, and because of reduction, there may be a potential difference generated. So that kind of potential difference is called reduction electrode potential. Or it is also called as reduction potential. That's it. Okay. And we have one more speciality here. For example, I have a metal, which is M. And if you put this metal M in its own electrolytic solution, the oxidation potential seems to be minus 0.14 volt. See, volt is the unit of any potential. Okay, it can be oxidation potential or reduction potential. Unit is volt. Okay. Some metal may have negative potential, some metal may have positive potential. See, from the sign of this potential, you cannot find whether there is oxidation or reduction potential. Some metal may have negative potential, some metal may have positive potential. Here I've given a hypothetical metal called M, and this metal M got oxidation potential as minus 0.1 volt. And you can convert this oxidation potential into a reduction potential just by changing the sign. That's it. So what will be the reduction potential of the same metal then? If minus 0.14 is the oxidation potential of metal, then what will be the reduction potential of the same metal?
Plus 0.14, ma'am.
That's it. Plus 0.14. For example, I have a metal N. And this N metal got oxidation potential as plus 0.95 volt. Then what will be the reduction potential of this same metal?
minus 0.95.
That's it. Minus 0.95 volt. So we can easily convert oxidation potential to reduction potential or reduction potential to oxidation potential. Conventionally, see, any metal in your problem, they may give you any metal and they may give you any potential. But conventionally, you have to use reduction potential for all the problems. Okay. So you have to use reduction potential in all the problems. Okay, which is very, very important for all the problems and for all the shortcuts I'm going to teach you in the future. You have to use reduction potential. Please don't use oxidation potential. You'll get confused. Okay. Most of the problem, they'll give you reduction potential only. If we are provided with oxidation potential, please convert that oxidation potential into reduction potential just by changing the sign, and then please proceed with your problem. Okay. Don't use oxidation potential in any of your problems and in any of your shortcuts. Okay. Please use reduction potential, and we can understand whether the given data is oxidation potential or reduction potential. To to identify that, I'll teach you how to identify all that. See, I have zinc 2 plus, and zinc 2 plus is gaining 12 electrons to get converted into zinc. Could you please tell me whether this reaction is oxidation or reduction reaction reaction?
Reduction, ma'am.
Reduction.
Reduction. So they may give you any chemical reaction. After giving the chemical reaction, they may give you the value like this. So since this is a reduction reaction, then we can understand this is the reduction potential. Okay, or they give you representation like this. E naught Zn2 plus slash Zn. See, here Zn2 plus is getting converted into zinc, which means by gaining electron, right? So from this representation itself, we can understand whether the values oxidation or reduction potential. You're getting my point. They may give you any reaction, they may give you the value from the nature of the reaction, we can find whether the value is oxidation or reduction potential, or most of the time they'll give you representation. From this representation, we can identify whether this is a oxidation or reduction potential. Now you have to tell me whether this is oxidation or reduction potential.
Oxidation potential, ma'am.
Very good oxidation potential. Could you please tell me the reduction potential of copper then?
Minus 0 plus 0.34, ma'am.
That's it. That's it. Okay. So, electrode potential is very, very important in this chapter. We may expect questions from electrode potential also. Okay. Do you have any doubt till now? Okay. See, initially we talked about the working principle of Daniell cell and we measured the cell potential as 1.1 volt, right? So measuring the cell potential is very easy. Just by connecting two electrodes through this voltmeter, we can easily measure the cell potential. But as far as electrode potential is concerned, we cannot measure the electrode potential as such. See, potential difference is nothing but we have to connect the positive terminal and negative terminal to voltmeter. So itself we had no issues. Both the electrodes were in solid state, so we easily connected the electrodes through voltmeter and we measured the cell potential, right? But as far as electrode potential is concerned, the potential difference is here, right? One is negatively charged electrode, another one is positively charged ions inside the solution. So we cannot connect these two steps. It is impossible. So just measuring the electrode potential is difficult or it is impossible. So if we have to measure any electrode potential, we cannot measure the electrode potential as such. You have to convert that electrode into a cell and you can measure it as a cell potential and not electrode potential, which is not very easy. See, I'll teach you, I'll tell you how it is possible. Here, I told you zinc and copper were connected, and both the electrode potential collectively it is 1.1 volt, right? For example, now this is my unknown metal, and I have to measure the electrode potential of this metal. And I have this metal dipped in an electrolytic solution, which contains M ions. Okay. Now, as I told you, we cannot measure the electrode potential as such, and I have to convert this electrode into a cell. So I have another electrode, and this electrode was again dipped inside its own electrolytic solution. And I'm going to connect these two electrodes using a connecting wire through voltmeter. Okay. And I have solved this and all that. Here I can measure the cell potential, but the problem is, for example, I'm getting the cell potential as 2.3 volt. But this 2.3 volt value is contributed by both these two. But we have to know the electrode potential of only metal M. But we don't know how to do that, right? So to measure the electrode potential of only this unknown metal, I'm going to have a reference electrode here. And we know the value of reference electrode already. For example, this reference electrode's contribution was 0. Okay, and I'm going to connect this reference electrode with this unknown metal. And the value here I'm getting is 2.3 volt means what it represents? 2.3 volt was contributed only from this metal M, right? And not from the reference electrode because reference electrode contribution was 0 volt, right? You're getting my point. You're getting the, you're understanding the role of the reference electrode now?
Yes, ma'am.
Yes, ma'am.
In chemistry or in electrochemistry, we have few reference electrodes, but in your syllabus, we have only one reference electrode, which is called standard hydrogen electrode. Standard hydrogen electrode, which is abbreviated as She. And the electrode potential of She is 0.0 volt. Since it is standard, I've represented it with naught. Since it is electrode, the representation is E naught, and the standard, standard electrode potential of She is 0.0 volt. You're getting my point now. So you can connect any unknown metal with She, and you can find the electrode potential of. Do you have any doubt till now?
No, ma'am.
Okay, fine. Fine. I'll show you the table column where we have measured the electrode potential of all the metals, and we have a complete table column for that. I'll show you that. Give me a minute. Okay. Is the screen visible? See, we have a tabular column where we have connected the unknown metal with She, and we have measured the reduction potential of all the unknown metals or unknown elements. For example, see, I have a reference electrode here. I have the reference electrode here, which is She. What is the value of She?
0.0 volt, ma'am.
Yes, 0.0 volt. And we have connected the all unknown elements with She, and we have measured the reduction potential. See, how do I found this is the reduction potential? How I'm telling these were reduction potentials? Let us say here. What is the reaction, Kanna? Ag plus is gaining electron to get converted into Ag, and parallelly they have given the value, right? So this value is basically the reduction potential. Okay. So in tabular column, we have reduction potential of all the elements with reference to your sheet. Okay. Right, Kanna? As I told you already, a few metals will have positive value, few metals will have negative value. Could you please tell me the reduction potential of chromium? Reduction potential of chromium. What is the reduction potential of chromium?
0.74.
Yes. Is it positive or negative?
Negative.
Negative. So minus 0.74 is the reduction potential of chromium. Okay. What is the reduction potential of copper 2 plus ion? What is the reduction potential of copper 2 plus ion?
0.34.
Plus 0.34. Okay. Next question you'll be having is whether you have to memorize these values. Please don't memorize it. In questions or in your exams, definitely they'll give you the values, and from the value we can proceed the problem. Okay. Please don't memorize these values. In exam, they give you the value. Okay. So our job is we have to infer the value and we have to do the problem. Okay. So in next class, we'll be discussing the physical significance, that is the importance of these values. See, initially how I've started, I've told you, among zinc and copper, zinc was oxidized and copper was reduced. And in your exams, they may give you two different metals and they may ask you which metal will get oxidized and which metal may get reduced, right? So to understand which will act as anode, which will act as cathode, this tabular column will be really helpful. Okay. And also we can use these values to calculate the cell potential. In Daniel cell, the potential developed was 1.1 volt, right? But in your exams, they may give you any random cell and they may ask you to calculate the cell potential. For that also, this tabular column will be very useful. For that, they will give you the values. From the values we can calculate. So we have so many physical significance of this reduction potential. One is you can understand which is anode, which is cathode, which metal will get oxidized, which metal will get reduced, which will act as oxidizing agent, which metal will act as reducing agent, and we can understand the direction of electron flow and the direction of current flow, and also we can calculate we can calculate the cell potential also. So we have so many physical significance of this electrode potential that we'll be discussing it in the next class. Okay. So let us recap the session. So we have started with the working principle of Daniel cell. We have discussed how this Daniel cell is actually working, how this chemical reaction is happening, and how this chemical reaction leads to current. And we have discussed what is electrode potential, different types of electrode potential, and how to convert oxidation potential to reduction potential, right? And what potential we are conventionally we are using in calculations?
Reduction potential.
Very good, reduction potential. Okay, right. So, do you have any doubt till now? If you have any doubt, please ask me now, or we'll wind up the session.
Thank you, madam.
No, ma'am.
Okay, okay, fine.
Hey,
Bye, guys. Bye, bye. Good night.
Rakshan,
Sir.
you said